a new version of alligator holes. All right, so our next speaker is Dr. excuse me, Dr. Dave Rudnick. Dr. Dave Rudnick has been focused on the needs of Florida Bay since his arrival 25 years ago. And he has been my confidant and good friend the entire time. He currently serves as the Everglades Science Coordinator for the National Park Service and as, and as Program Manager for the Critical Ecosystem Studies Initiative. We rely on Dave's critical ecological insight, and we tolerate his excessive wordiness. Dave's dig talk is entitled Salt, Fire, Water, and the Fate of an Ecosystem.
Thank you, Fred. I'll try to just be wordy and not excessively wordy. Okay, well, what I'm going to discuss today is basically the interaction of restoration and sea level rise, and how we can best realize our vision for Everglades restoration when facing the prospect of accelerating sea level rise. Sea level rise at a rate that potentially could inundate the area of Everglades National Park, much of it or most of it, by the end of this century. So that presents us with quite a challenge. How do we manage this large ecosystem in the face of such change? And how do we claim that we're capable of restoring the system? And short of just redefining what restoration success is, I want to consider what is our best path towards restoration success, regardless of those goals, to manage such a changing system. And I think I want to start with a premise, and that premise is that the Everglades ecosystem, the entire Everglades ecosystem, is built on a foundation of soils and the plant community that generated those soils. That is both a functional and structural basis for the system, and we need to pay attention to that. Any of our management actions for stewardship of this system and restoration of the system should strive to maximize the adaptation of the plant community to sea level rise effects in order to maximize the resilience of the system as a whole. And that leads me to what I'll call the kernel of a conceptual proposition as a pathway towards Everglades restoration success. And that is recognizing the pivotal the position of the coastal wetlands for the state of the entire system, that the trajectory of the coastal wetlands in the face of sea level rise will in large part dictate the trajectory of the entire greater Everglades system, both the upstream freshwater Everglades and the downstream estuaries and coastal waters. And that proposition is in large part, I want to thank many members of this audience who've contributed basically to our understanding of the system. So given that, I'll break this talk down into first, why is the mangrove-dominated coastal wetlands so important to the system as a whole? And then I want to discuss that basically there are three components that we need to pay attention to that can dictate the future of the coastal system. And those components are factors that we in large part can manage, can influence strongly, are salt, fire, and water. So what's so special about the coastal wetlands? Well, first with regard to sea level rise responses. And first and foremost is location. The coastal wetlands obviously are at the forefront, literally the front, of the defensive front of the Everglades to the sea. And the bounding trees you see here of mangrove trees have high resistance to ocean energy and provide some coastline, shoreline protection ecosystem services. But beyond just that, that front, immediately adjacent to the sea, the entire coastal wetlands, that enormous area that I showed in the previous map, which is about 500,000 acres just in Everglades National Park, this entire region provides critical ecosystem services that are highly relevant to the status of the adjacent freshwater Everglades and coastal zone. And foremost, just to, a thumbnail of this, those services are, first of all, binding, stabilizing soils. Second is sequestering, large stocks of nutrients and organic matter, materials. And third, gaining ability to gain elevation. The accretion of litter at the surface and growth of fine roots underneath can raise the elevation of the land itself. And I don't know, particularly for the freshwater Everglades, that anything is more important than elevation changes. To the extent we have subsidence, the sea level rise effects will be accelerated. The transgression of the sea inland will be accelerated. To the extent the land elevation increases, obviously it'd be the opposite, be slowed and be protective and slow the change with accelerated sea level rise, enabling adaptation of the upland system. For the downstream system, probably nothing is more important than the sequestration of nutrients and materials in the soils. If that enormous coastal wetland system is destabilized, the soils are destabilized, and especially when exposed to ocean energy, the transport of material seaward could be massive. The effects of the nutrients and particles be very detrimental to the system. I'll get into that a little bit more later. So given that, I want to shift now to why focus on salt, fire, and water. And I'll start with simply water. Again, returning to the theme of elevation, the simple hydration, the inundation of organic soils that are found throughout the greater Everglades system, not everywhere, but very, very widespread. Those soils are very vulnerable to drying, to microbial oxidation, and to fire simply by the absence of water, which we have created an absence of water in the Everglades starting 100 years ago or so. And our challenge is obviously with restoration, job one is rehydration of the Everglades. So this famous picture, I don't know that any picture illustrates the risk of drying wetland soils, organic soils. We're here 6 feet of loss in 80 years. It's pretty amazing in such a flat, low land. And this is indicative of what has happened historically in many areas of the Everglades, particularly the edges of sloughs. We have evidence that soil loss subsidence has been occurring and is occurring and may be accelerating in the coastal wetlands as well. This photograph from southern Shark Slough in the brackish marshes where a number of us are working shows the subsidence around a sawgrass plant with a loss of about 30 centimeters of soil. We don't know the time frame, but the plants aren't that old. It's a relatively rapid process. And we've termed this loss of organic soils in these coastal wetlands peat collapse. And it's not just in southern Shark Slough. This is a photograph, an image from the 10,000 Islands area. And there was a study there by Kim Andrus of Florida Gulf Coast University in her thesis, looking basically at the spatial analysis of ponds over a 60-year period. And this showed that a consequence of peat collapse, which is also demonstrated in the soil cores she analyzed, shows that over those 60 years, the size of those ponds has increased and the ponds have coalesced. Basically, the system is becoming more open. There's more open water. The system is converting from a grass-dominated and tree-dominated wetland into an estuarine open water system. And if and when those ponds are coalesced and are connected to the ocean, ocean energy will yield strong erosional forces that can even affect the system more. So, this is a real vulnerability of the system. better manage the system, we need to understand why, what causes this peat collapse, which appears to be widespread through the coastal wetlands. And towards that end, a large group of us, led by scientists from Florida International University, South Florida Water Management District, Everglades Foundation, and even the Park Service, have joined in to run multi-year experiments and several experiments, and students are to be applauded for their contribution here, graduate students, one Ben Wilson shown here, and run a series of experiments looking at dosing and controlling salinity exposure, drying, and phosphorus as potential factors that influence the incidence and the rate of peat collapse. And just quickly, some of the results. With salinization in the brackish marshes where there's still sawgrass, key finding is that salinization yields loss of root biomass with or without phosphorus. Also found, particularly in the field mesocosms, dosing sites, that there were large pulses of carbon dioxide from the soils and plants during a drought, during the 2015 drought. So there's a large loss of mass that way. And then finally, in laboratory mesocosm experiments, different soils, different experiments, but the finding is that with salt, and particularly with salt plus drying, there's a really amazingly rapid rate of elevation loss of centimeters per year compared to accretion rates that we typically expect elevation increases of maybe in a healthy system of 2 or 3 millimeters a year. So this is pretty striking. It's not to be extrapolated to what goes on in the field. It's an artificial experiment, but it still indicates the capacity for elevation loss that could be, be the defining. It is a defining characteristic of peat collapse. So what are the consequences of such peat collapse? Looking downstream, I think a great concern is the destabilization of soils via peat collapse. That material, the materials that have collapsed are going somewhere. They're not all going into the atmosphere. Very little CO2 will go to the atmosphere. Nutrients mostly are not. The particles are vulnerable to erosion, and dissolved organic and dissolved nutrients are going to move downstream into the coastal zone. To the extent peat collapse expands with accelerated sea level rise through this enormous coastal wetland, the material transport from the coastal wetland to the bounding sea and to our estuaries could be catastrophic, to use an extreme word. So we need to be cognizant of that and have some sense of urgency regarding measures to prevent that. Then finally, I want to talk about fire management. We influence our plant communities and influence their adaptive capacity via fire management. In Everglades National Park, there is a large fire management program that burns in the coastal wetlands at a frequency of every 3 to 6 years. The purpose is important. The objectives of that fire management program are, one, to prevent the ignition of peats in the dry season, particularly in droughts. So it's a fuel reduction program. And then second, to help manage the expansion of invasive exotic plants, particularly Lygodium, climbing fern, vine. A byproduct of this, though, a side effect, is that the fire itself, this fire frequency, is selective of the coastal marshes that are burned. The marshes remain dominated by grasses, and mangroves are not established to any extent in these marshlands, in these burned marshlands, and we're minimizing the establishment and expansion of such mangroves, and that's really an important consideration with regard to the building resilience of the system, and I would hold that based on the knowledge we have now, that enabling expansion of mangroves would be beneficial to the system as a whole. That those mangroves expand all the way to the freshwater wetland and beyond. Now, this could be considered enabling a mangrove invasion, But if you compare what's the cost of that versus enabling more peat collapse, elevation loss, and acceleration of sea level, of the inundation from the sea, I'd say that trade-off is there. So just in conclusion, we're not going to stop sea level rise. We have to manage it. And the way we can best manage is by increasing our freshwater flow significantly and potentially modifying our fire management practices to enable mangrove expansion. And that combination will help protect soils and particularly protect the elevation of those soils to slow the effects of sea level rise and protect the stability of the soils so that we don't have a large release of materials to the coastal zone. Thank you very much.